Welcome to section 4.2. The short version of this lecture is that everything you learn about limits and continuity for functions of one variable is still true. So now let's do the long version. Limits of functions of two variables. Let's start with a one variable function because that's something we're familiar with. If we want to take the limit as x goes to 0 of this function here, nothing bad's going to happen when we plug in 0 for x. So we're just going to do that. This is 2 plus the square root of 25 minus 0, which is 2 plus 5, which is 7. So what that means graphically is if we approach 0 on the x-axis from the left or right, the value of the function, the height of this curve, is approaching 7. Now, let's go to two variables. Suppose we want to find the limit as xy goes to 0, 0 of this function here. Now, using the graph, it looks like as we approach 0 in the xy plane, the height of the surface approaches 7. Well, let's see if that's what happens when we plug 0 in for x and 0 in for y in this limit. You get 4 plus the square root of 9. Square root of 9 is 3, so that's 7. So that's a little deceiving because it was so easy. You can approach 0, 0 in the xy plane many, many different ways. So we need a fairly involved definition of limit, and this is the precise definition of a limit right here, of a function of two variables. You don't have to memorize that and you won't have to use it. But at the end, I've got some examples of showing limits exist with that definition. Okay, limit laws, I'll let you read those. They're the same as they are for functions of one variable. And so let's just jump right in. Limit as xy goes to pi over 2, pi over 4 of this function here. If nothing bad happens, we can just plug in those two values. So this is equal to cosine of pi over 2 over 2 minus sine of pi over 4. Okay, the top is 0. I dropped the limit sign because I took the limit. That's when I plug in these values. And then on the bottom, I have 2 minus 1 over root 2, and 0 over a non-zero number is 0. So the limit's 0. It's that easy. Okay, next one, the limit as xy goes to 4, 4 of this function. Now when I plug in 4 for x, 4 for y, I'm getting 0 over 0, which is a do more work. And so there's more than one way to approach this, but I'll do it like this. This is the limit as xy goes to 4, 4 of, let's factor an x out of the top, x minus y, and then on the bottom I have root x minus root y, and that's, I'm just going to abbreviate the limit as lim, and I'm okay if you do that. So that's the limit as xy approaches 4, 4 of, let's write the numerator as root x minus root y times root x plus root y. So you might want to pause the video, make sure you believe that. Okay, and then in the denominator, we have root x minus root y. And now we can cancel those, and that's the limit of x times root x plus root y. Now I can plug in the values. X and y are both going to 4, so that's 4 times root 4 plus root 4, which is 4 times 4, which is 16. Okay, let's do one more. We could do this one very similarly to the way we did the last one, but I'm just going to change it up. I'm just going to write lim. I'm going to, actually, let me back up. When you plug in 2, 2, you get 0 over 0. So again, it's a do more work. But the work I'm going to do is to rationalize the denominator. So the way I'll do that is by multiplying this by the conjugate of the denominator, x plus y plus 2 root x plus y plus 2. Okay, now I'm just going to leave the top alone actually and write that as x plus y minus 4 times root x plus y plus 2. And then in the denominator, I'm going to use FOIL and multiply that out, get x plus y minus 4. Great. Now I can cancel, and that's the limit of root x plus y plus 2. And then remember, I'm going to 2, 2. So I plug in 2 for x, 2 for y. Square root of 4 plus 2 is 4. All right, last topic is showing limits don't exist. And so to do that, we need to be able to parameterize curves. And so I'm going to remind you of the parameterization Bible that we learned in Calc 2. And here are the 3 basic parameterizations that you use most often. And here's some examples. Let's parameterize the following curves. So y equals 3x falls under the category of functions. So we're going to let x be t and y be f of t, which is 3t. Yes, it's that easy. The next one, again, it's a function, so we can go t squared. And the last one is also under category 3. The x-axis is the curve y equals 0. So we can parameterize that by letting x be t and y be 0. All right, so now we can jump into showing limits don't exist. With a single variable, we can show a limit doesn't exist by showing the left-hand limit is not equal to the right-hand limit. So this is left-hand limit, this is right-hand limit. We can do something similarly in two variables. If we can find two curves in the xy plane such that the limit of the function over one curve is not equal to the limit of the function over the other curve, then we can say the limit does not exist. And that's basically the path test. So let me show you how that works with an example. We're going to show this limit does not exist by coming in at 0, 0 through two different curves in the xy plane and showing we get different limits. So for y equals x, first we need to parameterize that. That's t. Now for the limit, everywhere we see a t, everywhere we see an x, we plug in a t. Everywhere we see a y, we plug in a t. So this is the limit as t goes to 0 of t squared times over t squared plus t squared, which is 2t squared. So that's the limit as t goes to 0. So now we're down to a single variable of 1/2, because I canceled the t squares, and that's a half. Okay, now let's approach along the x-axis, which is parameterized by t0. So this limit is the limit as t goes to 0 of t times 0 on top, which is 0, and then t squared plus 0 on the bottom, which is t squared. Now, this is the limit as t goes to 0. 0 over a non-zero number is 0. The limit as t goes to 0 of 0 is 0. And these numbers are not equal, so we can say that the limit does not exist. Okay, continuity. Continuity works the same as it does with one variable. We've got a very similar definition here. And in your homework, you've got some problems where you're asked to find the set of points where a function is continuous. That's going to be the domain. So in this first one, natural log of negative 6x minus y is going to be continuous everywhere on the domain, which is negative 6x minus y greater than 0, which means y is less than negative 6x. All right, so negative 6x looks like this, and y less than that would be these points here. Those are the points where the function is continuous. All right, and last one, this function is continuous everywhere the denominator is not 0, so we need xy minus 1 not 0. So we need xy not equal to 1. So we need y not equal to 1 over x. 1 over x looks like this. And if the set of points where that function is continuous is all the points except those two dotted lines. Okay, and here's more reading. Just if you're curious how to use the actual definition of limit to find a limit, it's actually very difficult, and you will probably do that in another calculus class as you move on. All right, and that's the end.